actionable information. So is it correct information? This is just to assure you that it is. This is a paper we did in solar energy using 2 houses in Cambridge, one the MIT Student Center and a private residence. And we are within 3.6 and 5.3% of the actual prediction. So this analysis is very accurate. How well does it work on a larger scale? In order to understand that, we collaborated with the town of Wellfleet in Massachusetts, which is on Cape Cod, which some of you might know. And we worked there with the Mass Audubon Society, who in a solarized program. So they went to everybody in Wellfleet and said, get PV for your house, look at our map. And a lot of people did. Contacted the solar installers in the region. The solar installers discarded, by looking at the map themselves, 44% of the project because the roof wasn't ideal. And then when they actually went to a site, in 94% of the time the installers made a proposal. And the best part is that 54% of the time the proposal was accepted. So the rate was really encouraging. In 4 months, 10% of all the households bought a PV system. And this just shows you the advantage of getting information, unbiased information, to both sides, the client and the installers. So we are hoping in cities to create equal types of penetration over the years, but with more diverse technologies than this. And that brings us to UMI. UMI right now, if you want to use it in the urban planning or the architecture world, you can go to urbanmodeling.net, download it. It's a plugin based on top of a CAD environment that's widely used in urban planning and urban design called Rhinoceros 3D. When you open it, we are actually creating a kind of BIM database for a city. And then what you have to do is you draw a massing model of your city, buildings, trees, and streets. And we are converting that then in an energy model, for example, that allows you to do a very detailed analysis. So of course the question might be, especially if you have to BIM in that field, where usually people pay routinely $15,000 and more for an individual building model of a building, is this model any good? This is what I'll try to talk about in the next 10-15 minutes. So how does one actually build an urban building energy model? And I know there are quite a number of individuals in the audience that do similar work. We recently wrote a review on the topic, and I hope we didn't miss out anybody. If we did, it's completely wasn't intentional. So what are the key ingredients that you need to model the city? Well, you have to understand the weather and hourly data. That's a very well-established field. There are lots of databases for this available. You can combine this with urban heat island effect models. You can look at the future. That's a research branch in our field that has existed for a long time. And you can use similar tools at the individual building and at the city level. Then for the city, you also need the geometry of the city in sufficient detail. You then need what we call the non-geometric building properties. So you need to know all these things about that are hard to get. How is the city built? How is it being used? What kind of HVAC systems are in place? And you combine all of that in a simulation engine and get your output. So starting off with urban mapping models, where do you get that from? In the easiest case, in most of the Western world, you would get from the city GIS data, floor plans, and if you have the building height, then you can extrude that and you get this 2.5D massing models of the city. That's an easy start. These models often are not that good. Main reason is that people are not clear what the building height is. Is the building height the lower part of the roof? Is the top of the roof? That doesn't apply anywhere, but it's a good first start. Of course, when you look at innovation districts or new environments, you will often have something that you see on the right-hand side, so very detailed massing models that the urban planning office is providing for you anyhow. Now it becomes really academically challenging, or just technically challenging, when you're in areas where there is no GIS model. So we are building a model of Riyadh right now with 5 million people. I thought that was a big model, and then I heard Darren is modeling Shanghai with 24 million people, so I felt utterly inadequate this morning. But in Riyadh with 5 million people, there's no GIS, but lots and lots of LiDAR data. Because for the oil fields, LiDAR data is collected all the time because people want to know how the sand dunes move. LiDAR data stands for light detection and ranging. That's a technology where you fly with an airplane over an area and you collect point cloud data of these surfaces. So what we are working on with the Center for Complex Engineering System in a case like this is that we are creating, based on an analysis of LiDAR, three-dimensional models, such as the one you see on the right-hand side. So all of this to show is that in terms of geometry, we tend to have in most parts of the world sufficient data to create these type of models. How do we then do an energy model of the building? There are different philosophies. If you model an individual building, then you tend to build something that's called a multi-zone thermal model. That's something that you see on the left-hand side. You effectively take a building and break it into smaller zones and parts. And that can be a time-consuming process. One of the members of our group, Timo Dogen, who is now a professor at Cornell, developed this algorithm that we call the autozoner that can automatically generate a ASHRAE 90.1 Appendix G compliant energy model out of any form and shape that is possible. And you could, in this way, automatically, out of the massing models that I showed you before, create an urban energy model. The effort level for that is a little too high because the models would run too long. So what we are using instead is something that we call the shoeboxer. The shoeboxer is an approach where we are taking a whole city and breaking up in representative little shoebox models where one side touches the outside facade. It seems like a gross simplification of the actual thermal models that are used in practice, but we found that the approach at the urban analysis level works extremely well. So now we have nearly everything. We have the weather, we took that from other people, we have the massing models, we have a simulation engine. Now the tricky part is of course getting all this non-geometric building information. How will we be doing that? But starting off, at least we're trying to make the process as painless as possible by developing a data format that can be used by a lot of people so that if we've done it for one city once, we can do it again. The next step is to say we, of course, are not going to model every single building in the city, but we have to take a whole building stock and what has been traditionally being done to create archetypes where you group similar buildings together. And then you only need this input for one building at a time. Once you have this data combined, and we right now have archetype libraries for Lisbon, Portugal, Boston, and Kuwait, then you don't have to do the work again. If you have a city next to Lisbon, you could basically repeat that, and that way the effort you spend into building a building library the first time pays off. So this is the process of how you can create an urban building energy model. But now, of course, the question is how good are these models overall? So we have a workflow, but we have no idea if the workflow is any good. So in order to understand that better, what we did, we started off in Kuwait City in a neighborhood called Al-Qadsiya, where we looked at 200 buildings initially. And these were all single-family homes, or they call them villas there. You see Al-Qadsiya on the left-hand side. On the right-hand side, you see the energy use intensity distribution. That's the normalized energy use. And what you see here, which is of course something that we know from the past, even if you have the same type of building, occupant or resident behavior really matters. So in the same type of building, you get something from a respectable 50 kilowatt hours per square meter a year to an incredible 500 kilowatt hour per square meter a year. It's not even clear to me how one could get that high. But this is the reality of what you find in buildings. So this is what we want to recreate. So our first attempt was to just say we're modeling this neighborhood, one building type, one type of occupant, and then you see here in dark our energy use intensity distribution in dark gray, and in light gray you see the measured results. 15 minutes walk. Okay, so we weren't very close there. Then we went into the neighborhood, understood the building archetypes a little better. The building stock divided it into 4 different building types. And then we got 4 different building types, 1 type of occupant behavior. We got the spread a lot better. It got only really interesting when we started using a Bayesian approach to model occupant behavior in buildings. And the way this works is we use a sample of buildings and we create 800 different stories of how a building could be used. So we have families with lots of family members, high density in the building, and a lot of equipment, high thermostat settings, and we have all kinds of combination of those. Then we throw these different stories of the buildings for which we have measured data, and what we find is that only some of these stories stick. We don't know which of these stories are true because we can't go into the building easily due to privacy concerns, thank God, and figure out what's going on in the building, but we get likelihood distributions of behavior. And then we model, when we want to model a neighborhood, we model each building 100 times. That gives us an uncertainty for a building, and if we overlay that for all buildings, then we can create this variable. So in this first study we were cheating because the data that we used to calibrate our model and the test model were the same. So then in the next step we went outside of the neighborhood that we had looked at before, and we modeled other blocks, so different buildings, but we assumed the same behavior, and there our model still held very well. So then we went back to Cambridge, Massachusetts. We picked 400 buildings for which we had monthly energy data. We modeled 400 buildings, created our building behavior model, and then tried to model 2,500 buildings, different buildings. And again, as you see on the right-hand side, this works very well. So based on that, we know we have a technology that really allows us to pin down energy use distribution in a neighborhood. I quickly, due to the interest of time, go into more details. What this means is when you have annual energy data, then your calibrated model will also only be able to rightfully model annual energy use distribution. So you really have to fit your data. If you want monthly results, you also need a model with monthly data to calibrate your model to. And in Cambridge we showed that this is a poor fit if you use a model based on annual results to look at monthly energy use intensity distributions. You get way better results if you use monthly measurements. Okay, now we are in the invaluable situation that we actually have a couple of building models in the world that which are calibrated. What can the computer actually do now for us that we didn't know before? So the first thing was just looking at what-if scenarios. That was pretty standard. We worked in Kuwait City. We did a symposium for half a day last December. We invited key government officials and other industry stakeholders, and we showed them that for this neighborhood, if you put in off-the-shelf technology, you could reduce the energy use of that neighborhood by 85%. And that was really interesting because it allowed to highlight the opportunities that buildings offer to decision makers, and it also allowed them to develop aspirational goals. That's possible. Of course, one could say, well, do you really want to base your whole analysis on just 200 buildings? So in order to show that the same concepts already also work at a larger level, we worked last year with the Boston Redevelopment Authority and did an energy model of Boston with 80,000 buildings. Process is the same as you see here. We use the GIS data set. We automatically extrude it to find the number of floor areas, the number of where the windows are, where the neighboring buildings are. And then we run an energy plus model for each building in the city. And the main effort here was really to automate the process and make it so robust that you don't have to do anything by hand anymore. What do you get from that? Well, you can get this energy use distributions within a city. You don't learn too much because intuitively it's clear that the downtown core uses more energy than the surrounding. I think it becomes more interesting when you zoom into a neighborhood. This is Back Bay and Prudential Center in Boston. We actually look here at the hottest day of the year, so you see the electricity use simulation for that neighborhood on the hottest day of the year. And if you then say, well, what would happen to the distribution if we were to introduce photovoltaic production, then you get this famous duck curve. So in light gray, you see the current electricity use simulated. If you were to introduce a lot of photovoltaics, it's pretty well established. Then we know the two don't coincide in peaks. You get in the middle of the day PV, in the afternoon the air conditioning peaks. So you have this duck curve. That's very difficult for a utility to match this load profile. So what we looked at here, what would happen if we had a smart grid solution where the utility could relax the thermostat settings by about 3 degrees Celsius of every commercial buildings in the neighborhood. And the interesting part is really here, from a technological standpoint, if you follow these solutions, kind of you have one central controls for all the nests in the city, then you can dramatically reduce the peak loads. There are, of course, questions, very valid ones of privacy, but this is really provides you a framework to quantify the benefits of doing this. This project is something that I really like, from targets to reality, that was more zooming into a particular neighborhood in Boston called the Dudley Square neighborhood, and looking at energy use as well as census data. So based on census data, we can tell for every building block in that neighborhood who is living there, what's the educational level, what's the income level. We broke that whole neighborhood population into 4 types: elderly couples, families, young professionals, and students. We know the mix of those demographics within the neighborhood, and then we can do all kinds of analysis, starting off again with what's technically feasible. We developed for that residential neighborhood 2 sets of energy efficiency measures. Energy efficiency measures 1 is something that you can do anytime, such as changing light bulbs, weatherization, and then energy efficiency measure 2 was more comprehensive, low-end insulation, different HVAC equipment, and so forth. So we get the typical 17% and 60%. Now it becomes really interesting when you start combining what is technically feasible with actually who would have to implement what. So in green, for reference, you see the 2 goals for Boston. Boston wants to reduce carbon emissions by 2020 by 20%, by 80% by 2080, very convenient. And here you see, if you want to reach the 2020 goals, you need only to concentrate on homeowners in that neighborhood and have them put in energy efficiency measures 1 and 2. But the moment when you want to have more ambitious goals, you have to really start changing your energy incentive programs that exist in the world. We know in Massachusetts we have 92 different energy retrofitting programs. The uptake is very low, and it tends to be highly educated homeowners that do it. So you see very quickly that you don't get very far if you don't start changing this. So a few words beyond operational energy use. As I mentioned before, that we have various modules. So the, in quotation, easy module is once you have an urban database, is embodied energy. That's of course something I'm sure that has been covered here in the past days already. How much energy is required to construct, operate, and decommission a building. Typically, as a rule of thumb, many people say 85% of the energy of the building goes into operation, 15% into embodied energy. That's so low, we don't care. But as buildings become more and more efficient, that of course changes. So this is a study that we did a number of years ago in a neighborhood in Cambridge called Jefferson Park. It's an affordable housing community, very inefficient. And here you see 4 different scenarios for that neighborhood. And the kilowatt hours tell you embodied and operational combined for 15 years per square meter. So it's more of a comparison of the number that we should do. So 17,000 is the baseline, that's not doing anything and just leaving the buildings as they are. If we actually completely do a tabula rasa and rebuild the whole neighborhood in an efficient standard, we get to 13,350 because there's so much embodied carbon when we rebuild the neighborhood. So actually the best solution is just doing a facade retrofit and making a very focused improvement. And this is something that you find all the time, that the embodied carbon in our existing city is just so high that it's practically never worthwhile taking down a neighborhood and rebuilding that, especially if you think in terms of timing, that by the time when you break even, that's 80 years from today, and who knows what's going to be our planet at that point. Here just gives you an example how this would play out in Kuwait. Here, the neighborhood that you've seen before in Kuwait, if we were to change from in new construction the efficiency of the structure, so we use less concrete, then we go from the high red bar to the low red bar. If we substitute traditional concrete that they use with fly ash concrete, or if we replace the walls with earth walls, then you see we get lower and lower levels. So you can do this type of analysis as well. This has been traditionally a field that I have been focusing on, daylighting, access to daylight. That can, of course, also act as a placeholder for urban quality, health, and so forth. We developed a module that's again done by Timo Dogan that allows you to do annual energy use prediction at the urban level in short period of time. And in this year, we are celebrating the 100th birthday of zoning laws in New York City, which are pretty much the first ones in the world. So we picked 5 different growth archetypes for building blocks in Manhattan that we see here. So unfortunately, it's too dark for you to see the differences. We have the perimeter growth rate with the stencil towers and 5 different other ones, for which we are increasing the density. And we wanted to see if these type of urban typologies would be placed in Manhattan and surrounded by similar typologies, how much daylighting would we have? And here you see the results. This is terrible, you don't only see 2 results, but effectively we have a top line and a bottom line, and in total you see 5 for different types of urban photo blocks. And what one sees here, that it really matters, 5 minutes, perfect, that it really matters which type of urban prototype we use, how much daylight we end up with. So we want to stay above the red line, and we see in the case of the top stencil towers, we can get FARs of up to 25, which is incredibly high. If we actually want to compare that, an FAR of 12 is pretty much the maximum that you can build in Manhattan today. You see that if you use this typology, you can create a lot more real estate by still maintain access to daylight. If you convert that actually into money in Midtown Manhattan, the extra floor area that you can build if you would have this new zoning law is $1 billion per city block. And this, of course, is very important because we said at the beginning we need more city dwellers, so either we can spread out or we can densify. So we have to identify the winners in terms of densification that combine densification with good resourcefulness as well. Outdoor thermal comfort is, of course, key, linking into what I said earlier, because if we have more and more people in the city, then it matters more and more what the quality between the buildings are, and of course we heard from Stephen earlier that that's a key concern for many as well. In the past, what we've mostly done was very simplistic, just looking at outdoor temperatures and direct solar radiation to create hot and cold spots within the city. Now we just embarked on a 1-year-long study of the MIT North Court, where we are modeling for every hour, for every square meter in that North Court, for a whole year, the outdoor thermal comfort conditions, and at the same time we have various devices out with which we are tracking people moving through the space. So you get about 17,000 people moving through that space in a week. So that allows us to link resident flow to outdoor thermal comfort condition, and our goal is to basically test in how our current predictions are suitable and what we could do to have successful urban intervention to get more people moving through the space. And where does this all end to? These are my last couple of slides. Well, I'm a big fan of these scorecards where you basically present a neighborhood design or solution, and then you show the density, the cash flow, energy use intensity, daylight, comfort, and maybe other aspects of urban performance. And then you have an urban stakeholder debate. So in the case of Cambridge, Massachusetts, we modeled an area called Central Square, which is right between the Harvard and MIT campuses a few years ago. We had the existing conditions and then a city proposal to triple the density, and one of our proposals, which was just doubling the density but using micro units. And you can basically see how this financially that plays out pretty well, because smaller units charge higher rents, so that's a good thing. Having less built area also led to situations where you have more access to sunlight to the buildings, so better energy use, intensity, and more daylighting. So I like this type of comparisons because you can explain that in a very short period of time to non-experts, and then you can have a debate which of these trade-offs you are willing to do or not. In order to facilitate that more, we actually just built this UNI dashboard. This is a web-based platform which allows you to load in our UNI files right in there, and it shows you this type of analysis that I showed you before here in real time. And you can zoom in and drill in and understand your results better, because of course visualization is a key aspect of making a lot of people understand what you're doing. And this is just an example that I really like. This was done by a group of MIT and Portuguese students this spring, concentrating on Lisbon, where we looked at a neighborhood development in Lisbon, including, as you see from all the tomatoes here, how much food could we produce within the city. So we are here having a simple module that tells you basically how much tomato and other vegetables could be grown locally here through vertical farming. And this became really interesting because it shows you really the opportunities. People obviously used to live in cities based on food that was locally produced, so it's more than we think, especially if we use hydroponic types of technology. This project also showed you very nicely that at one point you have plants and photovoltaic competing for roof area, and then becomes an interesting discussion, what should be put on the roof. And technologically, it's pretty interesting. You can actually move something into the basement, and in some cases, it's better to have an urban plant machine in the basement fired by, supported by photovoltaic than actually have the greenhouse on the roof. So I think there's a lot of changing paradigms that we can look at right now. And jumping in the interest of time, two more quick projects that I wanted to show. This I show because it's my favorite one of all times. This was after the Haiti disaster. A group of MIT students used our tool with funding from Mercedes-Benz and the World Bank to develop for 50,000 people this disaster relief area. And they used the walkability module to place pumps and informal markets so that the neighborhood would be as connected as possible. And the reason why I like this because it just takes a laptop and a few gifted people to have an impact on so many people with practically no money. And this is the last project that I wanted to show. So one way is to say we are the urban experts, we are modeling 3 or 4 different variants of a city beforehand, and then we present that to the stakeholders. What we did here, this is a collaboration with the MIT Media Lab, the Changing Places group. We developed a real-time version of our UMI tool and linked it to a Lego table from the Media Lab. So what this table does is it's actually Lego pieces, and we have 18 different parts that you can put on the table. When you place this, we have a scanner from below that scans in the typology, feeds it into UMI, and then we are projecting in color on top of it the performance for daylighting, for energy, of our walkability of this neighborhood. And then we gave that for a whole day to the planning board in Rio to play with it and compete in 4 groups. And we turned off the sound, but you heard people arguing vehemently in Arabic about what solution for the neighborhood would be best. And it was just a fantastic experience to see in how far these type of tangible user interfaces are really good at engaging the creative potential of a lot of people at the same time. You obviously have to make some compromises in terms of detailing, but there's a lot of buy-in that you get. Last slide, Darren, closing thoughts. I think our urban performance analysis tools are now ready for prime time. We have the ability to use physics-based analysis tools to predict multiple levels of urban performance and can use them for meaningful new developments for neighborhoods. Now we really have to create and train a new breed of people. We need people that have an understanding of energy policy, urban planning, and of building physics. And if you combine all these qualities, then we can let them loose to the world. And at the same time, of course, we have to work with cities, practitioners, to explain to them what the capabilities of our tools are. And my hope is that these tools will be very widely applied in the near future, not by our groups and by a few of the groups that are at this conference, but by all the cities in the world. And with that, I thank you.